So in example 1 here, we have an EMF, in other words a battery or a voltage source, and it's connected to a circuit, right? And we have in this circuit a switch at point S that can be flipped to be connected between points A and B, right? And this changes the amount of the current through the circuit because it varies the potential loads. So, for example, in the first instance, the switch is open, and we see that, well, as shown, right? That switch is not connected to A or B, and so the circuit effectively has current flowing just along the outside. That's our current. I'll denote that by lowercase I. Current does not go into this path or into that path or even into this path here with R2, right? There's nowhere for it to go if it went in that path, right? It would effectively get stuck, right? So since nature likes to take the path of least resistance, that includes charged particles, it does not at all flow into those paths. Okay, so just around the perimeter. And also note that I've drawn the current direction by the popular convention that the textbook uses, not the actual direction that the current flows, right? So let's write out Ohm's law for this initial instance. We have the EMF, right, the maximum voltage that the current starts with, or rather the circuit starts with, and then traveling around, we next encounter the resistor 3. So that has a potential drop equivalent to the current times R3. Then we keep going past R3 in our loop here. Then we have current times R2, and then current times R1. And then we should be back around to the other side of the EMF, which means we're back at 0 potential. Okay? So you can start your Ohm's law equations like this, right? All terms on one side of the equal sign, or you can write them such that the EMF or any and all EMFs in the circuit are on one side and everything else is on the other, whichever way you prefer. And what I mean by that is, well, this, right? So it kind of separates the voltages from all of the other potential drops from the circuit elements. Okay, so if you do this, you have the EMF. I can factor out the current, and then we just have R3 plus R2 plus R1. And so what this problem is actually wanting you to do is to find R1, R2, and R3, the values for each of these three resistors. And so in this first instance, we can simply label this as, well, I'll say this is the equivalent resistance in the open case, right? And so the problem tells us that that value for the current when the switch is open is 1 milliamp. And so taking the voltage as 6 volts, we can find that. That gives us EMF divided by I. And in fact, I'm kind of running out of room here. We have 6 volts divided by the current. I'll put it in SI units, 0.001. And that's equal to that value, which is 6 kiloohms. Okay? And so this I'm going to circle as 1. Right? Keep that in mind. In fact, let me make that a different color. Let's put that in blue. Right? Let's remember this equivalent resistance in the open case. Okay? The second part of this problem is when the switch is closed to position A, the current in the battery is 1.2 milliamps. So let me draw that. Whoops, I'm still in blue. Let me draw the circuit in that case. When it's closed at position A, we have the resistor 3, We have the branch coming in, going up to point A. There's resistor 2, up to that node, over to R1, and back down to the battery. We also have this as a route. Okay, so it turns out we have, this was R3, R2, R2, R1, and the EMF again. So now when the switch is closed at position A, we actually have both resistor 2s in parallel with each other. And so the current loop would go like this, around, through R3, and then at this node it would split off. There would be a current that direction, and then a current this direction. And at this other node, they would recombine to go back into the battery. So let's write down the voltage again. So EMF minus IR3, and then minus the current, and I'm going to write that as an equivalent resistance of R22 minus IR1 equals 0. Okay, and doing what we've done in the past in part A, well, we have EMF, factor out the I's, and then we have an expression for the equivalent resistance. Notice I've done two things here. I've shifted the IR terms to the right side, and I've factored out the I term because the current is the same. Okay, it's the same value across all three equivalent resistors, meaning R3, R22, and R1. That's not to say that the value of the current in this loop is the same as the value of the current here. It's not, because the current indeed splits off. Okay, so that charge is effectively split. But that's not the same as what I have written here. I have that the equivalent resistance R22, the equivalent resistance of these two resistors in parallel, is the same as this current here and that current here. That is the same. And so now, doing what I did earlier, EMF over the current is now equal to that equivalent, which I'll call equivalent for position A, and that's equal to, what is it, 6 over 0.0012, and that's equal to 5,000 kiloohms, or rather 5,000 ohms. And so let's denote this as 2, right? This is our second equivalent resistance equation. And the third term, or on the third part in our problem, is when the switch is at position B. So let's draw that. This is a little bit simpler. At position B, right there, it actually skips R3. Right? And so at position B, the current follows the path of least resistance. So when the switch is closed at position B, right there, the current just goes whoop, and it misses R3 altogether. And so what we have is simply R2 and R1. And that's it. That's position B, and that's A, I guess. So this is slightly easier. We have the initial voltage, EMF, minus the voltage drop across R2, minus the voltage drop across R1, and that's back to 0 again. Okay, and so, whoops, EMF equals I now times R2 plus R1, and we can do a very similar thing. EMF divided by I, we know this value, or can calculate it. This I'll call R equivalent for part B, or rather connected to B. And so this is equal to, what is it, 6 over 1.002. Sorry, 0.002. There we go. And that's equal to 3,000. Okay. And so this is our third equivalent resistance expression. And so notice I haven't necessarily found the values for R1, 2, and 3 yet. I've just found the equivalent resistance in each of the three cases. So now, using the 1, 2, and 3 in blue, we can write a system of equations to find each of the individual resistances. So, what I mean by that is the following. That was equal to, I'll call it 6 kiloohms, and that expression was simply 1 plus 2 plus 3, right? Or rather, R1 plus R2 plus R3. The equivalent for switch position A was equal to 5,000 kiloohms, and that expression was R, I'll do it in numerical order, R1 plus R22, here we go. Whoops, let me just erase that. R22 plus R3, okay? And then R equivalent for part B was equal to 3,000 ohms, and that was equal to simply R1 plus R2, okay? Now, quick thing, we need to find out what R22 is, right? What the equivalent for that is. And remember, they were the same resistors, but just in parallel. So your intuition may tell you that they're the same, right? They're split equally. In fact, you'd be correct in that, okay? And we know that because resistors in parallel add inversely. So 1 over the equivalent resistance is the same as 1 over the individual resistors, like this, which is the same as 2 over R2. And so thus, inverting both sides, we have 1/2 R2. And there you go. So now I'm going to replace that. There we go. 1/2 R2. Okay? And so now we have a system of equations here. Right? We have a system of 3 equations with 3 unknowns, R1, R2, and R3. And because those that number is the same, this is solvable, right? In other words, we have the same number of equations as unknowns, thus it's solvable. So how do we do that? It may look a little intimidating at first, but with a little practice, you'll see that it's fairly straightforward. What you want to do is choose one of these equations, either that one, or that one, and just choose a variable to solve for, right? To get an expression for. Let me trim down the 6, 5, and 3 to ignore the units and just have the numbers, right? That may be a little bit easier. You could plug this into, I suppose, a Wolfram Alpha or the Mathematica, if you wanted to, but it's not that difficult to do it by hand. So let me choose the third equation, right? That is 3 equals R1 plus R2. And so I'm going to solve for, let's solve for R1. So thus R1 equals 3 minus R2. This is what I mean. And so this expression right here, I'm going to plug in to right there, the first equation for R1. And so that gives me 6 equals 3 minus R2, right? That was what we just plugged in. And then the rest of the first equation was plus R2 plus R3. Do you see what happens now? The R2 values, or those terms, cancel out. That's helpful. And so we're left with 3 plus R3. And now we have an equation just in R3 and we can solve. Thus, the value for resistor 3 is 3. Remember, the units are kiloohms. And there you go, right? We're 1/3 of the way done, so to speak. And so now, knowing this value, it makes our life easier when solving for R1 and R2. So now we can go back and plug this value here into either equation for R3, either that one or that one. It does not matter. Let's go and plug it into equation 2. It does matter. That's just the one I'm choosing. So we have 5 equals R1 plus 1/2 R2 and then plus 3 because we know that now. And so now we want to solve, can we solve for R1 and R2? No, we can't. Well, we just got an expression for R1. Let's plug that into this equation now too. And so what we really have is, let's see, 3, where do we go? 3 minus, whoops, R2, that was R1, plus 1/2 R2 plus 3, right? Yep. All right, and now let's try and reduce a little bit. Notice here we can combine terms, so we have 3 and 3, that's 6. I'm going to bring that to the other side. Well, actually, let me just rewrite this. We have 5 equals 6. Let's combine the R2 terms. This is minus 1 plus 1/2. This is plus 1/2 R2. No, negative. There we go. Minus 1/2 R2. And solving for R2, let's see, bringing the 1/2 on the other side, we have 1/2 R2 equals 6 minus 5 is 1. Thus, R2 is equal to 2. And remember, the units were actually kiloohms. Okay, so now we have 2 out of the 3. We can plug in this value into our third equation, and thus we have 3 equals R1 plus 2, and R1 equals 1 kiloohm. All right, and thus we found the actual resistance values for all 3 resistors. The physics part of it was all of this, right? Realizing how the currents behaved and the actual Ohm's law analysis for each circuit situation. That was the physics. If you have that part down, then you can realize that the equivalent resistance expressions from those Ohm's law equations can be combined into a system of equations, and from then it's just algebra. Okay, so that's how you would solve a system of equations from Ohm's law to find the individual resistances in a circuit. Thanks for watching.